Welcome to this problem walkthrough on LeetCode number 746, Min Cost Climbing Stairs. In this video, we'll explore an interesting dynamic programming challenge where the goal is to minimize the cost of climbing a staircase. We'll break down the problem, discuss multiple approaches, and analyze their efficiencies. Let's dive in. In this problem, we are tasked with finding the minimum cost to climb a staircase, where the cost of stepping on each stair is given in an array called cost. Each element cost, I, represents the cost of stepping on the ith stair. After paying the cost, you have two choices. You can either move up by one step or jump 2 steps forward. You can start your climb from either the first step, which is at index 0, or the second step, at index 1. The goal is to reach the top of the staircase with the least total cost. For instance, the input will be an integer array cost where the length of the array is between 2 and 10,000. And each value in the array is a non-negative integer between 0 and 999. The output will be a single integer representing the minimum cost to reach the top floor. Let's look at an example to understand this better. Suppose the input array is cost equals 10, 15, 20. The output in this case would be 15. Here's why: you could start at step 1, which has a cost of 15, and then take a single step to the top, resulting in a total cost of 15. Alternatively, you might choose to start at step 0, paying a cost of 10, and then jump 2 steps directly to the top, which costs 20 more. This path would give a total cost of 10 plus 20, which is 30. Since our goal is to minimize the cost, the best choice is to start at step 1 and take the single step to the top, making the minimum cost 15. Now consider another example where cost equals 1, 100, 1, 1, 1, 100, 1, 1, 100, 1. For the input cost equals 1, 100, 1, 1, 1, 100, 1, 1, 100, 1, the output is 6. Here's the reasoning: you could start at step 0 or step 1, and then follow the path 0, 2, 4, 6, 7, 9. On this path, the total cost would be 1 for step 0, 1 for step 2, 1 for step 4, 1 for step 6, 1 for step 7, and 1 for step 9, giving a total cost of 6. Any other path you choose would result in a higher total cost, so the minimum cost here is 6. As another edge case, consider the scenario where cost equals 0, 0, 0, 0. In this case, the output would simply be 0, because all the costs are 0, and there is no cost to climb regardless of the path taken. Now, let's revisit the constraints and edge cases to ensure the solution is robust. The length of the cost array will always be at least 2 and can go up to 10,000. So the algorithm must efficiently handle very large inputs without exceeding time or space limits. The values in the array range from 0 to 999, allowing for cases where some or all steps have 0 cost. When considering edge cases, think about the smallest input, such as cost equals 10, 15, where the solution must handle a staircase with only 2 steps. If all costs are 0, like in cost equals 0, 0, 0, 0, the result should be 0. Additionally, if all costs are equal, the algorithm must still find the optimal path. Lastly, for the largest possible inputs, the solution must be efficient and avoid unnecessary computations to meet the problem's constraints. To solve the min-cost climbing stairs problem, we first consider a brute force approach using recursion. The intuition here is to start at either step 0 or step 1 and calculate the minimum cost to reach the top. At each step, we explore two options: taking 1 step forward or taking 2 steps forward. The cost at each step is the current step's cost plus the minimum cost of the next 2 steps. This is implemented by defining a recursive function, minCost, I, that computes the minimum cost from step I to the top. The base cases occur when we either reach or exceed the top of the staircase. While this approach is straightforward, it has significant drawbacks. The time complexity is exponential, specifically O(2 to the power of n), because the function repeatedly solves overlapping subproblems. Additionally, the space complexity is O(n) due to the recursion stack. While simple, this method is inefficient and impractical for larger inputs, making it unsuitable for real-world applications. Recognizing the inefficiency of the brute force approach, we turn to dynamic programming, which leverages the overlapping subproblems of recursion. Instead of recalculating solutions, we store intermediate results in a DP array to reuse them. Here, we define DP, I, as the minimum cost to reach step I. The transition relation is straightforward. The minimum cost to reach a step is the current step's cost plus the smaller of the costs to reach the previous two steps, expressed as dp I equals cost I plus min dp I1 dp I2. We initialize the base cases with dp 0 equals cost 0 and dp 1 equals cost 1, and then iterate through the steps to compute dp I for each one. The final answer is the minimum cost of starting from either of the last two steps, which is min dp n1 dp n2. This approach significantly improves efficiency, reducing the time complexity to O(n). However, it requires O(n) space for the dp array, which we can optimize further. To make the dynamic programming approach even more efficient, we eliminate the need for a full dp array by observing that only the last two results are required at any given time. This leads to a space-optimized solution using two variables, previous 1 and previous 2. Initially, previous 2 is set to cost 0, and previous 1 is set to cost 1. As we iterate through the staircase, we update these variables for each step. The cost for the current step is computed using the transition relation, and the older values are shifted forward. After processing all the steps, the minimum cost to reach the top is simply the smaller of the values stored in previous 1 and previous 2. This approach retains the same O(n) time complexity while reducing the space complexity to O(1), making it both time and space efficient. It's an elegant solution that balances simplicity and optimality. Among the approaches considered, the space-optimized dynamic programming method stands out as the best choice. While the brute force method was discarded due to its exponential runtime, the standard dynamic programming approach, though effective, was further improved by reducing space usage. The key insight is that only the last two results are needed at any point, allowing us to replace the dp array with two variables. This optimization ensures that the solution is not only efficient in terms of time but also minimizes memory usage. For large inputs, this efficiency is critical, making the space-optimized DP approach the most practical and optimal strategy to solve the problem within constraints. To solve the problem of climbing stairs with the minimum cost, let's first understand the setup. You are given an array cost where each element represents the cost of stepping on a specific stair. Your goal is to calculate the minimum cost required to reach the top, starting from either step 0 or step 1. You can move up by taking either one or two steps at a time. To tackle this using a brute force approach, we define a recursive function minCost I that calculates the minimum cost to climb to the top starting from any given step I. If you're beyond the last step, no cost is incurred, making it a base case that returns 0. For all other steps, the function calculates the cost of stepping on the current stair, then recursively evaluates the two possible paths forward, one step or two steps. By taking the minimum of these two options, we compute the total cost for each starting point. This forms the foundation of the brute force approach. Once the recursive function is defined, we calculate the result by considering both starting points, step 0 and step 1. The result is simply the minimum of minCost 0 and minCost 1, which ensures we find the least expensive path to the top. While this approach explores all paths, it's important to think about edge cases. For instance, if the input array has only one step, the result is simply the cost of that step. Similarly, if there are two steps, the result is the minimum of the costs of those two steps, since you can start on either one. The recursive nature of this problem is straightforward, as each step depends only on the solutions of its subproblems, namely, the costs of the next one or two steps. However, this approach has exponential time complexity, 2 to the power of n, because it recalculates the same subproblems repeatedly. This inefficiency highlights the potential for optimization using techniques like memoization or dynamic programming. Examining the data structures and operations involved, we see that the recursion stack is a key component. It keeps track of intermediate computations as the function makes recursive calls. However, because this brute force method doesn't store intermediate results, it becomes highly inefficient for larger inputs. The input array cost, on the other hand, is used directly to access the cost values for each step. The recursive calls themselves are central to this approach, as each call splits into two branches, one for taking a single step and another for taking two steps. This ensures that all possible paths are explored. The base case is crucial for stopping recursion when the index goes out of bounds, and the min function plays a vital role in selecting the cheaper option at each decision point. Together, these operations form the backbone of the brute force solution, but they also underscore its limitations. To better understand the recursive process, let's walk through an example with the input array cost equals 10, 15, 20. Starting from step 0, you can either move to step 1 or step 2. To calculate min cost 0, you need the results of min cost 1 and min cost 2. Similarly, to compute min cost 1, you consider moving to step 2 or beyond the top, requiring the values of min cost 2 and min cost 3. Moving further, min cost 2 involves stepping beyond the top, where the base case ensures that no additional cost is incurred. By combining these results, we get min cost 0 equals 10 plus min cost 1, min cost 2, min cost 1 equals 15 plus min cost 2, min cost 3, and min cost 2 equals 20 plus min cost 3, min cost 4. The base cases min cost 3 equals 0 and min cost 4 equals 0 simplify the calculations, allowing us to determine the minimum cost for each path and ultimately return the minimum of min cost 0 and min cost 1 as the result. For the example input cost equals 10, 15, 20, the output is 15. The cheapest path involves starting at step 1 and moving directly to step 2, avoiding the higher cost of starting at step 0. Analyzing the complexity of this brute force solution, the time complexity is 2 to the power of n, due to the exponential growth of recursive calls, as each step branches into 2 more recursive calls. The space complexity, however, is n, which comes from the maximum depth of the recursion stack. To address the inefficiencies of this approach, we can apply optimizations. Memoization allows us to store the results of min cost I for each step, avoiding redundant calculations. Alternatively, we can transition to a dynamic programming solution, which computes results iteratively and reduces the space complexity to 1. While the brute force method is useful for understanding the problem, these optimizations are essential for handling larger datasets efficiently. This solution employs dynamic programming to efficiently solve the min cost climbing stairs problem. The key idea is to calculate the minimum cost to reach each step iteratively, using the results of previously computed steps. The function min cost climbing stairs starts by initializing an array dp of size n, where n is the length of the input list cost. This array will store the minimum cost required to reach each step. The base cases are straightforward. The cost to reach the first or second step is simply the cost of those steps themselves, which is stored in dp0 and dp1, respectively. The loop from index 2 to n1 calculates the minimum cost to reach each subsequent step. At each step I, the cost is determined by adding the cost of the current step, cost I, to the minimum of the costs required to reach the previous step, dp I1, or the step before that, dp I2. This ensures that the solution accounts for taking either 1 or 2 steps at a time. Finally, since the top of the staircase can be reached from either of the last 2 steps, the result is the minimum of the costs to reach these 2 steps, dp n1 and dp n2. This approach has a time complexity of n due to the single loop through the cost array, and a space complexity of n for the dp array. It is efficient and scales well for large input sizes. This is the Java implementation of the min cost climbing stairs problem. The solution mirrors the Python logic, using a dynamic programming approach where we calculate the minimum cost to reach each step iteratively. Key differences in Java include explicit type declarations, e.g., int, for arrays, and the use of Java's math.min method for comparisons. The base cases and iterative filling of the dp array ensure an efficient solution, with the final result being the minimum cost to reach the top of the stairs. To solve the problem, we start with the given cost array, 10, 15, 20. The first step is to initialize the dynamic programming array dp with the same length as cost, which is 3, and set all its values to 0. Next, we define our base cases. dp0 is simply the first cost, which is 10, and dp1 is the second cost, 15. At this point, the dp array looks like 10, 15, 0. Now, we calculate the minimum cost to reach each step starting from index 2. For I equals 2, we take the minimum of the costs at dp1 and dp0, which are 15 and 10, respectively, and add the cost at index 2, which is 20. This gives us 10 plus 20 equals 30, so dp2 becomes 30, and the array updates to 10, 15, 30. Finally, the minimum cost to reach the top of the staircase can either come from the last step, dp2, or the second to last step, dp1. Taking the minimum of these two values, min, 30, 15, gives us the result, which is 15. In this example, we have a more complex cost array 1, 100, 1, 1, 1, 100, 1, 1, 100, 1. The length of this array is 10, so we initialize the dp array with 10 zeros. Setting up the base cases, dp0 is equal to the first cost, 1, and dp1 is the second cost, 100. At this stage, the dp array is 1, 100, 0, 0, 0, 0, 0, 0, 0, 0. Now, we begin filling in the dp array starting from index 2. For I equals 2, the minimum of dp1 and dp0 is 1, and adding the cost at index 2, which is 1, gives us dp2 equals 2. Moving to I equals 3, the minimum of dp2 and dp1 is 2, and adding the cost at index 3, which is 1, gives us dp3 equals 3. Similarly, for I equals 4, the minimum of dp3 and dp2 is 2, and adding the cost at index 4, which is 1, gives dp4 equals 3. This process continues step by step, with dp5 becoming 103, dp6 calculated as 4, and dp7 updated to 5. The dp array progressively builds up as we calculate the minimum cost to reach each step. Continuing from where we left off, we now calculate the values for the remaining indices of the dp array. At I equals 8, the minimum of dp7 and dp6 is 4, and adding the cost at index 8, which is 100, gives us dp8 equals 104. For I equals 9, the minimum of dp8 and dp7 is 5, and adding the cost at index 9, which is 1, results in dp9 equals 6. At this point, the dp array is fully populated as 1, 100, 2, 3, 3, 103, 4, 5, 104, 6. To determine the minimum cost to reach the top of the staircase, we take the smaller value between the last two entries in the dp array, dp9 and dp8. The minimum of these two values, min, 6, 104, is 6. Thus, the output for this example is 6. Now, in this final example, the cost array is 0, 0, 1, 1, and its length is 4. We initialize a dp array with 4 zeros. For the base cases, dp0 is set to cost 0, which is 0, and dp1 is set to cost 1, also 0. At this point, the dp array is 0, 0, 0, 0. Starting from index 2, we calculate dp2 as the minimum of dp1 and dp0, which are both 0, plus the cost at index 2, which is 1. This results in dp2 equals 1. For I equals 3, the minimum of dp2 and dp1 is 0, and adding the cost at index 3, which is 1, gives dp3 equals 1. Now the dp array is fully populated as 0, 0, 1, 1. To find the minimum cost to reach the top, we take the smaller value between dp3 and dp2. The minimum of these two values, min, 1, 1, is 1. Therefore, the output for this example is 1. The time complexity of this solution is O, n, and here's why. First, we initialize a dynamic programming array dp of size n. Allocating memory for these n elements takes O, n, time. Then, we assign values to the first two elements of the dp array as part of the base case. Since these are direct assignments, they together take constant time, O1. Next, we have a for loop that runs from index 2 to n1, which means it iterates n2 times. In each iteration, we perform a constant time operation to calculate the value of dp I, using the formula min, dp I1, dp I2 plus cost I. When we multiply the number of iterations, n2, by the constant time per iteration, we get O, n2, which simplifies to O, n. Finally, the computation of the result using min, dp, n1, dp, n2, is a constant time operation, O1. Adding all these contributions O(n) for initialization, O1 for base cases, O(n) for the loop, and O1 for the final computation, we get an overall time complexity of O(n). The space complexity of this solution is also O(n), due to the use of the dynamic programming array, DP. Let's break this down. The input array cost is provided as part of the problem and doesn't count towards the solution's space complexity. The primary contributor to space usage is the DP array, which we use to store the minimum cost for each step. Since the size of DP is equal to the length of the input array cost, it requires n additional space. Other variables, such as n, the loop variable I, and any temporary values used during calculations, use a constant amount of memory, contributing only 1 space. Therefore, the overall space complexity of the solution is dominated by the DP array and is n. To understand the efficiency of the given solution, let's compare it with a brute force approach. A brute force solution would recursively explore all possible paths to reach the top of the stairs. This results in exponential growth of the recursion tree, leading to a time complexity of 2 to the power of n. Additionally, the recursion stack in the brute force method requires n space to account for the maximum recursion depth. In contrast, the dynamic programming approach we've implemented optimizes this by storing intermediate results in the DP array. This eliminates redundant computations, reducing the time complexity to n, while maintaining the same n space complexity. If we aim to further reduce memory usage, we can optimize the space complexity to 1 by storing only the last 2 computed results instead of the entire DP array. This would still result in n time complexity but with significantly improved memory efficiency. Now, let's analyze the best, average, and worst-case scenarios. Regardless of the input, the algorithm always iterates through the entire cost array, processing each step exactly once. This means the time complexity is n in the best, average, and worst cases. Similarly, the space complexity is n in all cases due to the DP array. Finally, let's reaffirm the time complexity mathematically. The for loop, which is the dominant operation, iterates linearly across the cost array, contributing n, while additional operations like initialization and final computation each add 1. When we sum these, we get n. For space, the DP array dominates with an n size, as other variables require negligible space. This confirms the space complexity is n. When solving climbing stairs problems, there are some common mistakes to watch out for. First, not handling the base cases properly can lead to incorrect results or runtime errors. For example, the initial costs at step 0 or step 1 are crucial for setting up your solution, especially when the input has very few steps, like just 1 or 2. Always verify these edge cases to ensure your solution is robust. Another frequent issue is relying on recursion without memoization. This can lead to inefficiencies due to overlapping subproblems, causing the solution to run in exponential time. To address this, make sure to use dynamic programming with memoization or tabulation. Finally, off-by-one errors in indexing are a common pitfall. Sometimes, the problem might use 0-based indexing, other times 1-based, or even require you to some costs starting from specific indices. Carefully read the problem statement to avoid these errors and ensure your implementation aligns with the requirements. Now, another issue to be mindful of is ignoring constraints on input size. For example, when the number of steps is very large, like n equals 10,000, a recursive solution without optimization can cause stack overflow or excessive memory usage. In such cases, iterative dynamic programming with space optimization is a better choice. This approach stores only the last 2 states, minimizing memory usage. Additionally, it's important to understand the problem's goal clearly. Some variations ask for the minimum cost to reach the topmost step, while others focus on passing the topmost step entirely. Misunderstanding this distinction can lead to incorrect results. Always revisit the problem requirements to confirm whether the final step should be included or excluded in your calculations. For interviews, climbing stairs problems often showcase key patterns that are valuable to recognize. Most of these problems boil down to Fibonacci-like recurrence relations, and identifying this early can help you avoid redundant computations. Be ready to discuss optimization strategies, such as the trade-offs between time and space complexity. For example, you might compare the n space of a full dynamic programming table with the 1 space of a space-optimized approach. Additionally, be sure to test edge cases thoroughly. This includes scenarios like minimal input, such as n equals 1 or 2, large inputs like n equals 10,000, cases where all costs are identical, and situations where costs include zeros or unusually high values. Testing these will ensure your solution is both correct and efficient. Climbing stairs problems often connect to other related problems, which can provide additional practice and insights. For example, LeetCode 70, Climbing Stairs, is a simpler version that focuses on counting distinct ways to reach the top without considering step costs. LeetCode 746, Min Cost Climbing Stairs, is the problem you're working on, where costs at each step play a role. LeetCode 64, Minimum Path Sum, extends this idea to a 2D grid, where you minimize costs while traversing from the top left to the bottom right corner. Finally, LeetCode 198, House Robber, is another dynamic programming problem with overlapping subproblems, where you must make optimal choices to maximize the total amount robbed while skipping adjacent houses. Exploring these related problems can help deepen your understanding of dynamic programming techniques and their applications. There are several approaches to solving climbing stairs problems, each with its own trade-offs. First, a recursive solution with memoization is straightforward to implement and ensures efficiency with a time complexity of O(n). However, it requires O(n) space for both the recursion stack and the memoization table. Next, iterative dynamic programming with a full table stores all intermediate results, making it easier to debug and visualize the solution. This approach also runs in O(n) time but uses O(n) space. For the most space-efficient option, iterative dynamic programming with space optimization reduces memory usage to O(1) by keeping track of only the last two states. While this method is less intuitive for beginners, it's highly efficient in terms of space. Understanding these trade-offs allows you to choose the approach that best fits the problem's constraints and requirements. Thanks for joining me in solving LeetCode number 746, Min Cost Climbing Stairs. Today, we explored dynamic programming as a strategy to solve optimization problems efficiently. Remember to practice similar problems to strengthen your understanding. Don't forget to like and subscribe for more helpful coding content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!